So last time we got to this stage where we're drawing tile map. The colours look a little wrong. I'll debug the graphics converter. I'm probably setting a bit wrong somewhere with the palette code, but we'll work with it for now. What we want to do now is look at some sprites. So what I've grabbed is the Pac-Man sprites. Again, these were already done from the Pac-Man arcade version. So these have been resized down to work with our graphic blocks, which were 6x6. These sprites are 12x12, except this larger Pac-Man, which actually for an intro, which we may use at some point, but for now all of these are 12x12. So the first thing we need to do is to use some of the new features we added into the graphic converter to start grabbing some of these sprites to draw. Set palette 0,0,0,0. I really want the first palette to be black. I don't know why, I just like it. We've now got the no reset. Load sprites. So I'm going to load the sprites. We're not going to reset the palette, so we keep the black as 0, and then we'll come to do the tile map. We're not going to reset it, and we'll grab everything after that. But for here, we need to grab some sprites. So we use our grab sprite. If we look back at our sprites, see you get 2 frames for each direction, plus the third frame is shared across all of them. So you'll go from semi-open, fully open, semi-open, circle, and repeat. So there's 4 frames of animation. But this circular frame is common to all of them. So we'll call this closed, and we'll want mask and data, because we'll obviously be masking these on the screen. We'll show you why in a moment. This is where we grab the first one, and then we want left 1, left 2, and I think we go up. So left, up, right, down. Oops. So it's left 1, left 2, up 1, up 2, right 1, right 2, down 1, down 2, and then we just need to change things. It goes, say they're all 12, they're all on 12 pixel boundaries, so it's 0, 12, 24, 36, 48, 60, 72, 84, and 96. So that should grab our sprites. Then we load the maze image, and we'll grab a maze. The one thing I haven't got at the moment, very easy, which again will, because we've been writing I've been writing the graphics converter, and are now starting to use it. There wasn't a huge amount of planning went into the graphics converter, other than it's similar to what I'd used before. But as I said before, I tend to have a generic tool for every project, but we're trying to make one universal one. I've only got output all, so all of the stuff is going to go out to one. Normally I'd have maze.s and I'd export the sprites to sprite.s. At the moment we can't do that very easily, but we'll add that at a later date. This will work fine for now. There's no reason why you can't have it all in one source file. I just tend to split it up. I'm also going to just rename the palette to game, just because it's not just the maze now. So there are all our sprites we're going to grab for now. Run the graphics converter. It's all happy. So if we go in here now, you'll see we've got sprite closed, sprite left, sprite right, and so on. The only other thing we need to do in here is up here we change the palette to game. So hopefully forgot to save it. So yeah, so they're all the same still. Good. Next bit of small housekeeping I'm going to do is I'm just going to create a new file called tilemap. I do tend to split things up into lots of files. It means you can just reuse the files time and time again. When you come to the next project, you don't have to start from scratch every time. So we'll put tile maps. This is the tile map handler. And I'm actually going to rename this to tile map render. And tile map draw 6x6. It's not hugely generic at the moment, because obviously we're in drawing 6x6, and as we said last time, usually the B8 by 8, something like that. We could store the width and the height. There's one thing we don't store with the sprites either, is we don't store the width and height at the moment, so we're very, very specific. But it's not a problem for now. I'm just being a bit... It's just how I tend to do things. I get a bit anal with setting out the code right. So again, hopefully, what we need to do is... I always prefer my data coming after everything else. Again, there's no reason, doesn't make any difference. Include the tile maps file. Good. So nothing's really changed, except it's a bit tidier. So yeah, so the next thing we want to do is we want to be able to draw a sprite. Let's use the closed frame. And we're going to use DE, we're going to load Pac-Man X. DE A and LDA cover. We're going to store two variables, Pac-Man X, Pac-Man Y, and they will be the position we're going to draw it, and then again we're going to hard code it. First things first, let's just do it there. Okay, so all we're going to do here is we're going to pass in the sprite, and we're going to pass in the X and the Y position. So if we go into our variables, we need to store our X and our Y for Pac-Man. Now, to render the sprite, it's very similar to rendering tile. So HL is going to be our address of the sprite data. D equals the Y coordinate. E equals the X coordinate. And what we could even do is go into a tile map, and we could probably pretty much grab that to start with. Now, we won't worry about storing the tile map. The first bit about getting the address is going to be slightly different. So what we need to do is work out the screen coordinates. As we know, the screens are 256 pixels wide, but there's 2 pixels per byte, so they're 128 bytes wide, which is a bit frustrating, because if it was 256 bytes, we'd just use D. We could just use D as the vertical position, but we need to divide it by 2. So divide that by 2. This obviously puts a 0 into the top bit, and then shifts it all down the bottom bit. So if we're on row 1, that 1 would shift off the right hand side when it goes into carry, and so then what we can do is get our X and bring in that again we shift it down and bring it in. At this point, the carry indicates whether or not the sprite is on the odd or even pixel. So if it's the carry flag is 0, we're on the leftmost pixel of the byte. If it's on 1, we should draw everything shifted 1 pixel to the right. Most games don't bother. You just do your horizontal movement in 2 pixels. It saves you a world of pain. The other thing we can do, which we might do, we'll see how things go and how things look. What we can do is store pre-shifted graphics. So effectively we double up all our graphics and we store a version already shifted 1 pixel. It means you don't have to bit shift things. You just have to use the carry flag to decide which frame to draw. But as I say, for now, we're going to stick with 2 pixels. An interesting thing here is obviously we're putting the screen into memory address 0 into the lower 2 pages. If you're writing this a different way around and you want to go into the screen to the upper 2 pages, there are versions of this that will shift carry in, so you can set the carry flag before you do this, before you do the shift. And so we can set carry flag, and we could do RRA, and then it would automatically set the top bit. It would do calculate the screen address, but automatically set the top bit as well. So yeah, if you're using page 128, using the memory pages CD, so 8000 hex onwards, it's a quick way of getting that address as well. But we're not, so we can just use that. As I say, our sprites are now 12 by 12, so what we could do, to be really horrible, as I said, we'll probably change the tile draw already, but just to show you, check it's working. We can just no, there's nothing wrong with this. I don't like it. It starts to get a bit untidy and it's not very efficient. It quite often is a trade-off between memory and speed. This uses a lot more memory, but it's faster than sitting in a loop in many ways. So there are times when yes, it can become useful to expand things like this. As I say, we're not going to do this. We'll change it in a second, but just as a quick test. Now this will not work for one very good reason. Oh, it's all corrupt. If you remember, we're grabbing the mask and the data because we're going to want to mask these sprites on and off of the screen. So we've got 2 bytes. We've got mask data and a graphic data. If we changed it just to data and make sure I saved it and rerun, if we were to do that, hopefully, there we go. We've got the closed frame. As you can see, there's a square. There's a black square around it. It's not doing a mask. Unsurprisingly, we've removed mask data. But that's why it was looking wrong with just that copy. So there is a better way of doing this. I'm going to put it into a loop. We could expand the loop. But what we'll do for now is we're going to do 12 pixels and we'll call this Y loop. Which we see it'll become 6 because horizontally there's 6 points. And then we call this X loop. Read a byte from the screen. So we get the screen data in. Mask out the areas for the sprite. So we use our mask data, or in the graphics, and write it back to screen. Peter Gallagher has done a good little article on this masking, so I recommend digging that up if you want some more details. But essentially, you're just clearing out the areas that we want to put the sprites in and leaving the areas we don't. We can do that, and then we can DJNZ X loop. So we'll do all the X pixels. We still need to step to the next row of the screen. Any of this. Okay. And now we need to do all the vertical. Okay. Hopefully, should now have. 100 minus 6 was doing 6 bar. Helps we step to the next row of the screen. Ooh. Still got something a little wrong somewhere. We're stepping right, it's actually just the source graphics. So we're loading in. Did we grab it? We did grab mask and data. Did we revert graphics? Nah, I just haven't reconverted the graphics. That's fine. So yeah, so you can see now the background is still visible around the edges. We haven't got a horrible black square. So that's good. So we're effectively drawing a sprite. As I say, there's probably a fast way. Well, there are fast ways of doing it, but if we were to now put that draw in here and do X, increase A, Pac-Man X. So we're now going to move it each time. It's going to go quite fast because we haven't got anything to slow it down. There we go, you see. Obviously, one thing we're not doing is clipping, which is useful because clipping is a bit of a pain. The problem with clipping is if we're storing our X position in a byte, 0 to 256, that's fine because it's 0 to 255. The problem is if we want to step off the right hand side of the screen effectively by 1 pixel, we need to say our X position is -1. -1 is 255. So are you drawing it 1 pixel off the left, or are you drawing it right at the right hand side of the screen? Screens do wrap, but you need to know so you know which way to clip. So you can store the X as a word and do it that way. Different projects do different things. Dizzy uses, because it moves in 4 pixels, it stores everything as base off every 1 X position increment is actually 4 pixels on screen, so they only need 64. 0.64 to represent the entire movement across the screen, and they start in the middle. So there's lots of different tricks. We could use, we don't need to clip, so we don't need to worry. We could always use X divided by 2 because we're doing 2 pixel steps. But yeah, it's just something to be aware of. Maybe at some point we'll cover some clipping techniques. It'd be nice to slow this down a bit. We can't use halt, which is quite useful until we put an interrupt system in. I don't really want to put an interrupt system in now, so let's do a horrible delay loop for now. PC can be or CJR not 0. Come on, delay. Okay, hopefully that might give us enough of a delay. Yeah. You can instantly see one problem. We're leaving a trail. because we draw the sprite, masking with what data is already on the screen. We move the sprite, we draw it again. So we need to clear it. What we can do, which is very nasty, actually probably the easy way of doing that is to move. We could just redraw the map every time. We won't need this delay loop now, this will be very slow. And yes, we're not leaving a trail, we're flickering horribly because we're taking so long to draw the map and we're not double buffering. So without double buffering, redrawing the entire screen is, as we can see, slow, nasty, not the way to go around it usually. You could stop the flickering, we'll say, with double buffering. We will add double buffering, but not yet. So we know that's not the way to go. So let's not do that. We'll leave our delay loop in because we want to see what's going on, otherwise it goes too quickly. But yeah, so we need to remove the trail. If we can't redraw the entire screen, it makes sense just to redraw the part we're so what we shall do is we need to store the data. We'll just call this Pac-Man store. It's 12 by 16, 12 by 12 or 12 by 6 bytes. So we've got 72 bytes. We will actually have a better system. This is because obviously we'll have the ghosts and everything, but for now let's just create a store big enough for that. I'm going to use 100 bytes because I need a bit more data, as we're about to see. So if we get our background store and I will put in here. I'm going to put in 255 to say there's nothing there. We can't restore it the first time in because we haven't rendered the sprites, so we've got nothing to draw, so we need to know what we can do. The usual process would be wait for the end of a frame, swap buffers if we're using double buffers, and then we will clear off all the old graphics and then draw them in their new position. So what we need to do here is we now need to store it. We could pass it in a BC. Pac-Man store. But that's not going to be very helpful when we get in here because we're using BC for loop counters and other such things. So if we think about it from when we're drawing, we could use IX. IX is quite slow, unless you really have to. I wouldn't recommend, because we're reading the screen here, we could store it, but I wouldn't recommend using IX. Bizarrely, it's actually quicker to store the screen data replacement. It takes 4 cycles. I think it's 19 cycles to load A into IX and 10 cycles to increase access, 29 cycles. EXX 4 cycles from memory. So we've switched to alternate pair. We can stick it into H. I think it's like 6 or 7, and EXX. It's a little bit quicker to do it this way. It may even be quicker to do the entire loop twice. First time running through, grabbing the screen, second time through, doing all the actual drawing. I'm going to do it this way for now. So what we need to do is we need to put the store into the alternate pair. So EXX. We will, when we come to do multiple sprites, we won't pass it in every time because what we'll have is a long list of everything that needs to be restored. So, but for now, we will just pass it in. So this is HL dash equals background store. address to store replacement graphic background. Oh dear, graphic. Okay. Now, storing all data is all very useful, but we need to know where to put it. Now, we could store the X and Y, but then we have to do all this. We've conveniently got the address we want to store it. So, we need to store, we're going to push the address onto this background store as well. Customary to use little endian first, but because I want to know when the end of the store is there, the low byte being the address is always can be anything. So it would make it hard that the fact we've used 255 to indicate when we've finished drawing everything. So what we want to do is store it in reverse order. So store the address to restore to. The problem is we use exx. Annoyingly, DE disappears as well. We could do it numerous ways. I'm just going to stick it on the stack and bring it back off the stack. And then into HL, I'm going to put D to begin with. And then I'm going to put E. It's not ideal. It's a little bit cumbersome, but it will do. And then every time we draw some screen, we're going to store this graphic. As I say, first thing we want to do, this itself won't do anything different. All we're doing is storing it. What we now need to do is wait for the delay, clear the graphic, then draw the new one, then draw it in its new place. You'll notice we didn't have to, because we are remembering the address of the screen to replace the graphics, we don't need to store the X and Y, therefore we don't have Pac-Man old X. Because otherwise we'd have a problem if we tried to restore it to Pac-Man X and Y, because obviously we've changed it. So, but we stored the address. So let's erase all sprites. So node HL with Pac-Man store, pull sprite, erase all. And that'll be a little function down here. And that is the address of the restore buffer. Now, read on thing, read the first byte, compare with 255, and return if it's 0. So first thing we'll do is check we've got some data. We do, so get the address in DE. So remember this was the wrong way around. We've stored the high byte first, so we can have 255 as the end indicator. Replace 12 by 12 pixels. Again, we could store the width and the height. At the moment, all our graphics are 12 by 12. We might even be cheeky. What we could do here is cut this up. This is actually 24 by 24, so we could actually cut it up and draw 4 12 by 12 sprites, and then we don't have to do any different sprite routines at all. Might do that. Anyway, so for now we just need to replace 12 by 12, so we can just do attempt to even we could do it in one big loop. It's a Y loop. LD that makes no sense. So let's use C there, because we'll need to redo this. So 6. This is the X loop. So we want to LDI. In fact, let's just do again. Not nice. We'll change on these later, but it'll do what we need to do. Put that to B, because it upsets B, we will BC, place graphics, pop BC. Of course, the one thing we have to do here is now exchange DHL LD BC, 128 minus 6, add HL BC, exchange D HL again. Still need to step down to the next line of the screen. Oh, I thought underscore was the. I'll have to check what PyZ80 uses. Some of them have a variable symbol you can use for local variables that would be relative to this. Might be dot. I won't know because I haven't got any other dot ones in there at the moment. There we go. Ooh, that's not working. 1, 2, 3, 4, 5, 6, and go through 12. Let's have a look. Probably forgotten something. Pac-Man store. Ooh. What we will need to do at the end of. Oh no. I think we'll need to put an end terminator in, but we won't because we're only raising one at the moment. So first time in, Pac-Man store is going to contain 255, so we'll early out, otherwise we'll load. We haven't moved on. So there you go. What we're doing now is moving it. When we get to this edge of the screen, yeah, so what we're doing is we've got a bit of a delay loop. We could take the delay loop out. But as I say, because we haven't got anything else, it'll go very quick. Doesn't go that quick at all. Oh, I've got to save it, I was going to say. I was expecting it to go quicker than that. Yeah, a bit too quick. So there you go. You'll see it's flickering because we're not double buffering, so it's sometimes we're catching it clearing out with the redraw. So we now got a sprite routine. We can position our sprite wherever we want. We could, for instance, we could make Pac-Man 15, put the white 15. And it shouldn't matter. Our system should just handle drawing and drawing. So that's good. Put that back to 0. One other quick thing we'll cover. I will put it in for now. We want to terminate the sprite redraw. Because what we will be doing is rendering more sprites, so we will need to erase more. So what this will, the background list will just become a list of address data that it needs to restore. And so 255 will be used. So what this will do, instead of here, it will be JR So if it's just a long list of addresses with 255 at the end, this will just keep looping around, grabbing the address, replacing the 12 by 12 data, and go back for the next one. So this should still work as is, because all we've done is we've just added a terminator onto the sprite redraw. There you go. But now this redraw system is completely ready for when we draw more than one sprite. We need a little bit of updating in here, because obviously at the moment we're always passing the same address. What we would normally do is quickly do it now. Let's put, it's 72 plus the address, 74 bytes per sprite, plus a null terminator at the end. 74, let's say we have 10 sprites. So let's do 704. Let's do 1k of background store. And this is the current address. So what we'll do up here is we'll go background store, put the null terminator in, and then remember the current address. So this is set this up to the beginning. When we want to restore, we erase them all, reset the store address, and every time we draw a sprite, we can just grab the store address. We won't even do this in here. Oops. Grab the store address, put the graphic in, and once we've done the store routine, we can now say we've terminated it. We don't need to increase HL before we do this, because this is the null terminator. The next sprite would overwrite this with its own address, so we just store that there. Should work as exactly the same. But what we could now do, just to have a bit of fun, there's nothing stopping us. I think we'll do left one. Let's just have a check. Just put a different address. Hopefully. There we go. We've got two sprites moving around. Masked. Restoring. Animations won't be hard. We'll leave that there for now. But next time we'll tidy up the code a bit more. We'll move these sprite routines into their own sprite routines. We'll probably put an interrupt routine so we can look at animations. And also I'll show you a nice trick. The problem with double buffering is when you're restoring 2 frames ago, where at the moment we just restore the previous data. But there's a nice trick we can do, which means we don't have to do any horrendous code. It all just magically works. So yeah, I'll show you how we'll do that next time when we have the double buffering, interrupts and animations. But for now, I think it's a good place to stop.